Normally when we think about using an app, there's this underlying expectation of magic.
Oh, absolutely. It feels completely effortless.
Right. It's like turning on a faucet. You tap an icon on your phone, the little wheel spins for, I don't know, a fraction of a second, and suddenly your food is ordered, or your ride is waiting outside, or
Or a 4K movie just starts streaming right into your living room. We've been completely conditioned to just assume it all exists in the cloud, ready and waiting for us.
yeah, ready and waiting. But then you actually step behind the curtain into the world of software architecture. And suddenly, that seamless magic trick is revealed to be this chaotic, massively complex global factory.
It really is. It's a digital landscape that is mind-bogglingly intricate, and yet it's completely invisible to the average person.
Exactly.
Okay.
So today, for all of you listening, we are going to explore that invisible architecture. We're diving into system design. We have this massive, comprehensive transcript here from a system design course, and our mission today is to extract the absolute essentials.
Because, frankly, anyone with a weekend to spare can write a piece of code that works perfectly for 10 users.
Right. I could probably do that.
You definitely could. But what happens when 10 million users log onto WhatsApp or Amazon at the exact same millisecond? Why doesn't the entire internet just collapse into dust?
That is the multi-billion-dollar question, isn't it?
It really is. Because when you transition from a handful of users to a global scale, the fundamental physics of your software completely change.
Reading through these sources, this whole concept actually reminds me of a bank. So let's imagine a physical brick-and-mortar bank. We'll call it Alien Bank.
Alien Bank, I like it.
Yeah. So inside this bank, there's exactly one cashier taking care of customers. And immediately, we have a bottleneck.
A huge one.
Right, because the process is painfully slow. Let's say this cashier takes 10 minutes per customer. They're manually counting cash. They're writing out paper receipts by hand. I mean, if you're running this bank, you can only serve 6 customers an hour.
Which is a failing business model. If you get a sudden rush of 30 people on a Friday afternoon, your system essentially crashes. The line goes out the door, people get angry, and they leave.
Exactly. So you have to fix it. And your first instinct is probably to train the cashier. You teach them to type faster. You optimize how they speak to customers so they don't chat as much.
Right. In the software world, this is the equivalent of improving your code quality or your algorithmic efficiency. You go into the back end and tweak your data structures so your software runs leaner and faster.
But there is a ceiling there, right? I mean, eventually your cashier is working as fast as physically possible.
Yes, you cannot optimize a human being or a piece of code, for that matter, beyond the laws of physics. They can only move so fast.
Which brings us to the second issue. The bank is getting popular. The cashier is blazing fast, but the line is still out the door. So we upgrade their environment. We give them a state-of-the-art cash counting machine. We build them a bigger, better desk.
We give them a faster computer.
Right. And this is what the sources call vertical scaling.
Yeah, vertical scaling is simply taking your existing single server and beefing it up. You buy more RAM, you slot in a faster CPU, you get a larger solid-state drive. You are making that single machine as powerful as a machine can possibly be.
But wait, even a superdesk has limits, right?
Sure.
I mean, I can only plug so many cash counting machines into one wall outlet before the breaker trips.
Exactly.
So eventually the line is still too long. Our highly trained, heavily equipped cashier is totally maxed out, and you cannot make them any faster. So what do? You are forced to hire a second cashier. You build a second desk, and this is horizontal scaling.
Right. You are adding more machines rather than bigger machines.
And reading this, it feels like that's the moment everything gets complicated.
It is. If we connect this to the bigger picture, and this is a recurring theme, you'll see this is the fundamental truth of all system design. Biological systems, like the human cardiovascular system, they're pre-built by needs, and they already scale naturally as we grow. But IT systems are engineered by humans from scratch. So every single time an application scales, whether you're training the cashier or adding a second one, a new bottleneck is immediately created somewhere else.
Oh, that makes so much sense. Because if I add a second cashier, suddenly they both need to know exactly how much money is in a customer's account at the exact same time.
Exactly.
Like if a customer deposits $10 with cashier 1 and then immediately walks over to cashier 2 to withdraw it, cashier 2 needs to know about that $10 right that second.
Yeah.
They can't just have their own separate paper ledgers. They need a shared ledger.
Which introduces the need for a centralized database. And furthermore, think about the front door. If every customer walks in and just lines up at cashier 1 because they happen to be closer to the entrance.
Cashier 2 is just sitting there doing nothing.
Exactly. So now we need someone standing at the door directing traffic. A middleman, which is a whole other layer of complexity.
Wow, okay. But before we start building these massive multi-server alien banks, we actually have to figure out what kind of heavy lifting our system is going to do in the first place, right? I mean, you can't just buy a bunch of servers without knowing what they're actually supposed to process.
It's the most crucial first step. If you misidentify the fundamental nature of your application's workload, you will bleed money on infrastructure that doesn't actually help you.
And the sources break this down into two main categories, which I found super helpful. Data-intensive applications and compute-intensive applications.
Yeah, let's unpack data-intensive first.
Okay, so this is all about the movement and storage of massive amounts of information. You're focusing on concurrent reads and writes. I'm thinking of something like an Instagram feed or WhatsApp. The sources noted WhatsApp handles, what, millions of messages a day?
Over 2 to 10 million a day, depending on the region, yeah.
But the bottleneck there isn't complex math, is it?
No, not at all. When you send a photo on WhatsApp to your family group chat, you aren't asking the server to solve some complex algebraic equation.
Right.
You are simply saying, take this 1 megabyte file, find these specific 50 people in a massive database, and push the file to their phones as fast as physically possible. The challenge is entirely logistical. It's about data movement.
So the bottleneck is the database, or literally the network cables themselves.
Exactly.
Okay, so on the flip side, we have compute-intensive applications. And these are bound by the CPU, or the GPU. The actual volume of data might be tiny, but the mathematical calculations are incredibly heavy. The example that really stood out to me from the notes was a flight simulator.
Oh, that's a perfect example.
Right, because in a flight simulator, you aren't downloading terabytes of data from the internet every single second. But your local machine or the server running in the cloud is doing massive parallel processing to render the physics of the wind against the wings.
It's calculating gravity, drag, thrust, weather patterns, all in real time and 60 frames a second.
Right. And that distinction completely dictates where you spend your budget.
It has to. If you have a data-intensive app like a messaging service that's running slowly, and you go out and buy the fastest, most expensive CPUs on the market, it won't help you at all.
Wow, really?
Yeah, your incredibly fast processors will literally just sit idle, twiddling their thumbs, waiting for the slow hard drive to find the data. You need better databases, you need more caching, faster network infrastructure.
Okay, and conversely, for a compute-intensive app, all the fast network cables in the world won't help if your processor can't crunch the numbers fast enough to render the next frame of the simulation.
Exactly.
Okay, but what about something that lives in the middle? What about YouTube? Because obviously it's pushing massive video files, but it's also running that crazy algorithm to keep me watching videos until 3 a.m.
YouTube is a hybrid. It's a great example. Serving the actual 4K video file to your television is heavily data intensive. It requires a massive global network of storage. But the recommendation algorithm, the artificial intelligence, figuring out exactly which thumbnail will keep you on the platform based on your past 10 years of viewing history, plus the viewing history of millions of similar users, that is wildly compute intensive.
So you really have to dissect your app feature by feature. You can't just slap a label on the whole company.
Exactly.
Now, once you know if you're dealing with a data mover or a number cruncher, you have to define the requirements. Our sources divide these into functional and non-functional requirements.
This is a classic distinction in software engineering.
Right. So functional requirements are literally what the app does. Like a user can search for a product on Amazon, they can add it to a cart, apply a coupon code, and check out.
And non-functional requirements dictate how the system performs those functional actions.
Okay, wait, let me see if I can ground this. If I'm thinking about a restaurant, the functional requirements are the menu. It's what I can actually order: a burger, fries, a shift.
Good analogy, yeah.
And the non-functional requirements are the invisible things that make the restaurant actually run, like the fact that my food arrives in under 15 minutes, or the fact that the kitchen can serve 1,000 people a day without catching fire, or that the health inspector gave it an A rating for safety.
Exactly. Translated to tech, non-functional means handling 1 million daily active users without the server crashing. It means keeping latency, which is the delay before a transfer of data begins, under 200 milliseconds.
Right.
It involves defining SLAs or service level agreements where you legally promise your corporate clients 99.99% uptime for the year.
But practically speaking, for everyone listening, if you're sitting down to design a system, how do you actually know if a specific feature is data or compute heavy? Is there like a quick test?
There's a brilliant rule of thumb from the sources. Ask yourself, is the time being lost in data movement or in computation? If your app is lagging because it's waiting for information to travel from a hard drive to RAM or from a server in London to a phone in New York, it's data intensive. If it's lagging because the processor is pinned at 100% trying to calculate a result, it's compute intensive.
That is such a great lens to view it through. Saves millions in server costs if you get it right. Okay, so we know what our app does, we know the menu, we know the kitchen requirements, but honestly, none of that matters if a user's phone can't actually locate the app on the internet in the first place.
This is a big one.
Yeah, we have this global web of billions of devices. How does my phone find your specific server in, say, Virginia?
This is where we have to bridge the gap between human language and machine language.
Yeah.
Because machines don't understand names.
Right. When I type google.com into my browser, my computer has no idea what that means. It doesn't speak English. It speaks in numbers. It needs an IP address, something like 192.168.1.1. So we use DNS, the domain name system. But a question I had while reading this, why can't my browser just download a master list of every website and its IP address, like a digital phone book stored locally on my hard drive? Wouldn't that be way faster?
It sounds faster in theory, but there are over 350 million registered domains today. Your browser would grind to a complete halt trying to search a text file that large every single time you clicked a link.
Oh, wow. Yeah, that would be a massive file.
And more importantly, IP addresses change constantly. Servers go down, traffic gets rerouted, companies switch hosting providers. If you had a static list, half the internet would be broken for you by tomorrow morning. So the system has to be distributed and dynamic.
So how does the journey actually work? Because when I hit enter, it feels completely instant to me.
It's a massive invisible relay race. Let's trace it. You type in Amazon.com. The very first thing your browser does is ask your operating system, hey, do you know this IP?
Okay, and if not?
If not, it asks your internet service provider's DNS resolver.
Okay, so that would be like Comcast or AT&T or whoever I pay for Wi-Fi.
Right. And if they don't know, they go to one of the 13 root servers in the world. These are the absolute backbone of the internet, categorized A through M.
Wait, only 13? That sounds incredibly fragile. Like a bad storm could take out the whole internet.
Well, there are 13 logical root servers, but they are physically mirrored across hundreds of locations globally for redundancy, so it's very robust. Now, the root server doesn't know Amazon's exact IP address, but it looks at the URL and says, this ends in .com. Let me send you to the top-level domain server, the TLD, that handles all .com addresses.
So it's narrowing the search area, like going from the country to the state.
Exactly.
Yeah.
Then the .com TLD server looks at the request and says, I don't have the IP, but I know who manages Amazon's domain records. It directs your request to the authoritative name server, usually hosted by AWS or a registrar like Route 53.
Okay.
And that server finally looks at its ledger and hands over the exact IP address.
That sounds exhausting. I mean, imagine doing a global relay race for every single image, every script, every font on a single web page. The page would take minutes to load.
Which is exactly why caching is absolutely critical here. At almost every step of that journey, the IP address is memorized or cached for a set amount of time.
Oh, I see.
Yeah, your browser remembers it, your operating system remembers it, your ISP remembers it. So the next time you type that URL, it skips the global treasure hunt and just uses the saved IP.
Okay, so DNS gets us to the correct front door. We have the IP address.
Right.
But once my phone connects to the server, how do they actually talk to each other? Like, how does my banking app talk to the back-end mainframe? Or how does a movie app pull actor ratings from IMDb?
They use APIs, application programming interfaces.
Right. And our sources list several types. There's SOAP, which is older and uses XML. There's gRPC, developed by Google, which uses protocol buffers.
Let's define that, actually. Protocol buffers are a way of serializing structured data. Instead of sending raw text, gRPC compiles the data down into a binary format.
Which makes it faster.
Incredibly fast, which is why it's mostly used for internal microservices talking to each other inside a company's private network. It's too rigid for public use, but perfect for back-end speed.
Got it. Then we have WebSockets, which create a real-time, two-way open channel. That makes total sense for a live chat app or a multiplayer game where the server needs to constantly push data to the user without being asked.
Yeah, WebSockets are essential for real time.
But the absolute king of the hill, the one that dominates the modern web, is the REST API.
REST is the bread and butter. It relies on standard HTTP methods.
Right. You have getT, which fetches data,
Huh?
post, which creates new data, delete, which is pretty obvious. But then you have PT and patch each. And reading the sources, the distinction between those two seems both vital and, frankly, incredibly easy to mess up.
It is a classic trap for new developers.
Mm.
Both are used for updating existing data, but they do it very differently. booty replaces a record entirely. PTH only partially updates it.
Okay, let's play this out so I really understand it. Suppose I have a user profile on an app. It have my username, my age, my email, and my address. And I want to change just my username. If I use a POKCH request, I just send the new username, and the server updates that one field and leaves my age and email alone.
Exactly. It patches the specific hole you pointed out. But if you use a PUT request and you only send the new username...
Wait, the server takes my partial request and replaces my entire profile with it.
Precisely. A PUT request says, here's the complete new version of this object. So if you leave fields out, the server assumes you want them empty.
So my username updates, but my age, email, and address are overwritten with blank values, effectively erasing my data.
Yes. It is a very fast way to accidentally delete user data.
That is terrifying. Okay, so when you send these requests, the API talks back using status codes. We're all familiar with the classic 404 not found, but the sources outline a whole ecosystem of these codes.
Think of the server as a highly rigid, slightly bureaucratic desk clerk. You hand it a form, and it stamps a number on it to tell you how it went.
I love that analogy. So the 200 series is the clerk giving you a thumbs up. 200 means okay. 201 means created successfully, like you just registered a new account. But then there's 204, which means no content. Why would I want no content? Is that a glitch?
Not at all. A 204 is common when you successfully delete something. You tell the clerk, destroy this file, the clerk destroys it and stamps 204, meaning it's gone, I have nothing left to show you.
Yeah, that makes perfect sense. Okay, then the 300 series R redirects the clerk saying, we move that department down the hall, go here instead. But then we get to the errors, the 400s.
The 400 series means you made a mistake. The client is at fault. 400 is a bad request. You filled out the form wrong. Maybe you missed a required field. 401 is unauthorized. You didn't show your ID. You need to log in.
And 403 is forbidden. Which is interesting because you did log in, but the clerk says, I know exactly who you are, but you don't have security clearance for this specific file.
Exactly. You're logged in as a normal user trying to access admin settings, for example.
What?
And finally, the 500 series. 500 means internal server error. The clerk looks at your perfectly filled out form, turns around to file it, and the entire filing cabinet is on fire. It's the server admitting, it's not you, it's us, we messed up.
So structuring these API requests is a whole art form in itself. Our sources emphasize how a well-designed REST API should be intuitive just by looking at the URL. They brought up nested URLs versus query parameters.
This is about defining relationships cleanly. If there is a direct hierarchical relationship, you nest it. For example, the URL user's 123 comments is very clear. It's asking for the comments that belong specifically to user ID 1223.
But wait. What if I don't want a specific user's comments? What if I want to see a list of every comment ever posted on the entire site, but I only want to see the ones posted in the last 24 hours, and I want them sorted alphabetically? How do I write that?
That is exactly where you use query parameters. You don't use slashes for that. You would hit the main comments endpoint and add a question mark, like .sort elfentime 24 hours. You are filtering a massive data set, not exploring a hierarchy.
But here's a detail from the source that I found totally fascinating. When the API finally responds and sends that list of comments back to your phone, it should always be wrapped in a JSON object, which uses curly brackets, never a raw array, which uses square brackets.
This is a huge best practice.
But why does that matter? If I ask for a list, why shouldn't the API just hand me a list?
Because of future-proofing. Let's say you build an app and your API returns a raw array, a simple list of 50 users. The app launches, it's successful. A year later, the business team comes to you and says, we want to display the total user count at the top of the screen.
Okay.
If your API is returning a raw array, it can only hold list items. You literally have no place to put the number total count, 5,000, without breaking the array structure and crashing older versions of your app.
Oh, but if I had wrapped that list in a JSON object from day one, it's like putting the list inside a manila envelope. I can always slide an extra sticky note into the envelope later.
Exactly. You wrap it in an object. Key one is data, which holds your array of users. Key 2 is metadata, which holds your total count, your pagination links, server timestamps, whatever. You can add as many new keys as you want in the future, and older versions of your front-end app will just ignore the new keys without crashing.
That is such a smart architectural decision. It costs nothing upfront, but saves you a massive headache later. Okay, so the API successfully brings the data into the server, but where does it actually live? When an app scaled from hundreds of users to millions, how you store this data becomes literally a matter of survival. This brings us to the database tier, the eternal battleground. SQL versus NoSQL.
It is the most fundamental choice in back-end design. It dictates everything else you do.
Let's start with the classic, SQL, or relational databases. When I read about this, it just sounds like a highly organized, heavily militarized Excel spreadsheet. It's strict, it's table-based with rows and columns, and it enforces rules, which we call constraints.
Right. You can enforce that a specific column must be unique, so no two users can register with the exact same email address. Or you can enforce not null, meaning a field cannot physically be left blank by a user, but the true power, the reason they are so popular, lies in their relationships.
Hence, relational database. You use primary keys to identify a specific row and foreign keys to link it to another table, like a one-to-many relationship, one user writing many blog posts, or many-to-many relationships.
Many-to-many is tricky. Think of a university database. You have many students and many courses. A student takes multiple courses, and a course has multiple students. To make that work in SQL without creating massive redundant data, you actually have to build a third table in the middle called a junction table.
A junction table, okay.
Its only job is to map student ID 5 to course ID 10. It just holds IDs.
That feels a bit clunky, having to build an entire table just to act as a bridge. But I saw another relationship trick that made total sense. One-to-one. If I have a table of blog posts, and some posts have massive, high-definition video files attached, the source suggested separating them into two tables. Why?
Performance. If you keep a 1 gigabyte video file in the exact same row as the text of the blog post, every time someone searches the database for a specific word in the text, the database engine has to lug those massive video files into memory just to scan past them. It's wildly inefficient.
Oh, that makes sense. So you create a separate table just for the heavy media files, link them one-to-one with a foreign key, and suddenly your text searches are lightning fast because the main table is featherlight.
Exactly. But before we move on, we have to talk about why SQL is so trusted. You mentioned earlier it's strict. That strictness is defined by ACID properties.
Right. ACID. Just to ensure we're completely grounded here, what exactly is making these transactions so bulletproof?
ACID is an acronym: atomicity, consistency, isolation, durability. Let's focus on atomicity because it's the most critical. It means a transaction is all or nothing. Imagine you are transferring $100 from your checking account to your savings account.
So standard banking transaction.
Step 1, the database deducts $100 from checking. Step 2, the server loses power and crashes. If this database wasn't atomic, you just lost $100 forever. It vanished into the void.
Ouch.
But because it is atomic, when the database reboots, it realizes step 2 never finished, so it automatically rolls back step 1. Your $100 is safely returned to checking.
It guarantees the money doesn't just evaporate.
Yeah.
And then consistency ensures the database rules are never violated. Isolation means if two people try to withdraw the same $100 at the exact same millisecond, they get queued up. They'll both get the money. And durability means once the transaction is complete, it's permanently saved to disk, even if someone kicks the power cord out.
Which is exactly why every bank, every payment processor, every financial ledger on Earth uses relational, ACD-compliant databases. You don't mess around with money.
Okay, so SQL sounds perfect. It's safe, it's organized. But then we have NoSQL non-relational databases. And these are schemaless. They don't force you into rigid tables.
And because they don't force rigid structure, they are incredibly easy to scale horizontally across multiple servers.
There are a few flavors here. We have key value stores. This is the simplest. You give it a key, it gives you a value. No tables, no columns. It's incredibly fast, perfect for caching. Then we have columnar databases. This one blew my mind a bit. Instead of reading data row by row, it reads column by column.
It's an analytic superpower. Let's say you have a database of 10 million users with 50 columns of data, each name, address, phone number, and finally, total spent. If you want to find the average total spent across all users in a traditional row-based database, the engine has to load all 10 million rows into memory, read past the names and addresses just to get to that one number.
Which would take forever.
But a columnar database, like Amazon Redshift or Google BigQuery, stores each column separately on the hard drive. It just goes straight to the total spent file, grabs the numbers, and calculates the average instantly.
That is so cool. Then there are graph databases, nodes and edges. The source compared it to a detective's string board, where photos of suspects are connected by red yarn. The nodes are the suspects, the edges are the relationships, and both can have data attached to them. This seems incredibly niche.
It's niche but powerful. If you are building a recommendation engine like users who bought this also bought that, or trying to detect a fraud ring where 50 different accounts are all secretly funneling money to the same offshore bank account, a relational database would choke trying to join that many tables.
Right, the junction tables would be insane.
A graph database spots the visual web instantly. It's designed for it.
And finally, document databases, like MongoDB. They store data as JSON-like objects. And this brings us back to the Instagram feed. If I scroll my feed, one post is a video, the next is a photo album, the next is pure text with a poll attached. A strict SQL table would be a nightmare here. You'd have 100 columns, and 90% of them would be empty for any given post.
A document DB just says, throw the whole object in. I don't care what shape it is, I'll store it.
But wait, I have to push back here. If NoSQL is so incredibly flexible, so fast, and can scale across 100 servers with the push of a button, why doesn't everyone just abandon SQL entirely? Why deal with rigid tables and junction tables at all?
Because in system design, there is no free lunch. The trade-off is strict consistency. We talked about ACID properties for SQL. NoSQL, generally speaking, relaxes those properties to achieve that incredible speed and scale. It trades strict instant consistency for what we call eventual consistency.
Eventual consistency, meaning it will be right eventually, like maybe not this exact second.
Exactly. If you like a photo on Instagram, that data is written to a NoSQL database in California. It might take 2 or 3 seconds for that to sync over to the database in Europe. For those 3 seconds, the databases disagree. But who cares? The world won't end if your friend in London doesn't see your instantly.
But if my bank delays updating my balance for 3 seconds and I make another purchase in that window, I could overdraft my account.
Exactly.
So use SQL for your money, use NoSQL for your memes.
That is a very accurate, if slightly reductive way to look at it, yes.
Okay, so we've got our database securely storing millions of records. But we have a new, terrifying problem. Imagine 10,000 users just logged on at the exact same second to view the home page of our e-learning site. The page displays the top 10 most popular courses. If the backend queries the database 10,000 separate times for the exact same top 10 list, the database will overheat and crash. It's doing the same work over and over.
We need a shortcut, and that shortcut is a cache. Caching is the act of storing frequently accessed data in a very fast temporary memory layer, usually RAM, sitting right in front of the database.
But wait, if caching is so fast, why don't we just make the cache bigger? Why not put the whole database in RAM and never touch the hard drive again?
2 reasons. First, RAM is astronomically more expensive than a hard drive. Second, RAM is volatile. If the server loses power, everything in the cache is instantly erased. The hard drive is permanent, so the cache has to be temporary.
Right. And because it's small, data goes stale, so we use TTL time to live, an expiration date on the cache data. The sources outline 4 main strategies for how data flows through a cache. First is read-through. The app asks the cache for the top 10 courses. If it's a cache miss, meaning the data isn't there, the cache itself turns around to ask the database, saves a copy in RAM, and hands it to the user.
And then the next 9,999 users get the lightning-fast cached version.
Exactly. Then you have write-through. When an admin updates a course name, the system writes the new name to the cache and to the database at the exact same time. It ensures the cache is never holding stale, wrong data, but it adds a slight delay to the write process.
Next is write around. This is interesting. Writes bypass the cache entirely and go straight to the database.
Why would you do that? Isn't the point to use the cache?
Think about uploading an archival log file or an old invoice. You are writing the data once, but you are highly unlikely to ever read it again immediately. If you write it to the cache, you are just filling up your expensive RAM with useless files, pushing out the important stuff. Write around protects the cache from being flooded by dead data.
Ah, that makes perfect sense. And finally, write back. This is wild. You write a change, it hits the cache, and the cache instantly tells the user, success, data saved. But it actually hasn't saved it to the permanent database yet. It waits and updates the database asynchronously in the background.
It's risky, but incredibly fast.
The source used food delivery apps like Swiggy or Zomato as an example. Think about it. When a restaurant taps a button to update your order status from cooking to out for delivery, they need that button to respond instantly, even if there are a million concurrent orders happening globally.
They read it to the cache.
Right. If the server crashes a microsecond later, your order status might revert back to cooking for a minute. It's annoying, but speed beats strict consistency in this scenario.
But again, cache memory is small. It fills up. And when it is 100% full, you need an eviction policy, a rule book for what gets deleted to make room for new data.
The most common is LRU, least recently used. The example given in the notes was perfect. Apple announces the new iPhone 17. Suddenly, everyone is searching for it.
Yeah.
No one is searching for the iPhone 11 anymore. So the cache looks at its memory, sees the iPhone 11 data hasn't been requested in a week, and deletes it to make room for the iPhone 17. It ditches what hasn't been used recently.
Contrast that with MRU, most recently used.
This one messed with my head initially. Why on earth would you delete the data you just used a second ago? But then I thought about a video streaming buffer.
Yes, walk through that.
If you're watching a movie on Netflix, and you just finished watching the first 10 seconds of a scene, you are highly unlikely to immediately rewind and watch those exact 10 seconds again. You need the next 10 seconds. So the system deletes the 10 seconds you most recently watched to clear RAM for the upcoming frames. It's a continuous conveyor belt.
You also have LFU, least frequently used, which tracks how many times an item was accessed over its entire lifetime, not just how recently. An item might not have been touched today, but if it was accessed 10 million times last month, LFU will protect it.
Okay, so the cache is shielding the database from being crushed by read requests. But what is shielding our actual web servers? Remember the alien bank. We added a second cashier and we realized we needed a middleman at the front door to direct traffic so one cashier didn't get overwhelmed. That middleman is the load balancer.
The load balancer is the unsung hero of the internet. It is the traffic cop. It sits between the open internet and your private fleet of servers, routing requests, and constantly performing active and passive health checks.
I picture it exactly like a genius bouncer at a busy nightclub. This bouncer doesn't just check IDs. They know exactly what's happening at every bar inside the club. They know which bartender is currently the least busy. They know which bartender makes complicated cocktails the fastest. And crucially, if a bartender suddenly passes out, the bouncer instantly notices and stops sending thirsty people to that bar.
And they use specific algorithms to make those routing decisions in milliseconds. Let's walk through them because they illustrate the complexity of managing chaotic traffic.
First is round robin. It's the simplest. Customer 1 goes to server A, customer 2 to server B, customer 3 to server C, and customer 4 loops back to server A. It's perfectly equal distribution.
But there's a glaring flaw there. The bouncer is ignoring capacity. What if server A is a brand new massive supercomputer and server C is an old laptop from 2015? Round robin will crush server C.
Right. So we upgrade to weighted round robin. You explicitly tell the load balancer, server A has 3 times the RAM of server C. Send 3 requests to A for every 1 request you send to C.
Then there's geo-based routing. This is pure physics. If a user is logging in from Mumbai, India, route their traffic to the servers physically located in Mumbai, rather than a server in California. You are literally reducing the distance the light has to travel through the fiber optic cables, which cuts latency.
Next is least connections. The bouncer looks at the servers and says, who is helping the fewest people right now? If server A has 10 active connections and server B has 50, send the next user to server A. But even that can be deceptive.
It can. What if server A's 10 connections are massive, complex video uploads that are pinning the CPU at 100%? And server B's 50 connections are just tiny, lightweight text messages. Server A has fewer connections, but it's actually drowning.
So to fix that, you use the least time algorithm. The load balancer constantly measures the average response time of every single server and routes the new user to whoever is currently replying the fastest. The sources noted this is absolutely vital for high-stakes, low-latency applications like stock trading platforms where a millisecond delay can cost millions of dollars.
And finally, IP hash. The load balancer takes the user's IP address, runs it through a mathematical formula, and the output dictates which server they go to.
Why do that?
It guarantees sticky sessions. If the math sends you to server B on your first click, the math will always send you to server B on your 100th click.
So if I'm shopping and server B is remembering what's in my shopping cart locally in its own memory, I need to make sure I don't get routed to server A on my next click, or my cart will suddenly be empty.
Exactly. But sticky sessions are incredibly fragile. What happens if server B catches fire? The load balancer reroutes you to server A, but server A knows nothing about your cart. You lose everything. This is exactly why modern architecture pushes towards stateless servers. You shouldn't keep the cart data on the server. You should keep it in a centralized shared cache like Redis so any server can handle any request at any time.
That makes total sense. Decouple the memory from the processor. Okay,
Yeah.
so the load balancer fixed the server traffic jam. The caches are protecting the database from read requests. But what happens when our central database is now physically holding 100 terabytes of data? It is literally out of hard drive space, and it's choking on write requests. We've hit a wall.
When a single database hits its absolute physical limit, you essentially have two options left in system design. You clone it, or you slice it up.
Let's explore cloning first. This is replication. It solves the single point of failure and drastically increases how many read requests you can handle. The most standard setup is single leader. You have one master database, the leader. All the write requests creating a new user, posting a tweet, changing a password go exclusively to the leader. The leader then copies that new data to all the follower databases.
And here we run into a major timing dilemma: synchronous versus asynchronous replication.
Right. If I update my profile picture and the leader waits for all 5 followers across the globe to confirm they received the new picture before telling me upload successful, that's synchronous. It's incredibly safe, but brutally slow.
Too slow for the modern web. If even one follower has a network hiccup, your app hangs and the user just sees a spinning wheel forever.
So the industry standard is asynchronous replication. The leader writes the data, instantly tells the user upload successful, and then updates the followers in the background a few milliseconds later. But this introduces a terrifying risk: stale data. If I post a tweet and then my phone immediately refreshes by reading from a follower database that hasn't received the update yet, my tweet vanishes. It looks like it was deleted.
It's the trade-off for speed. But an even bigger question is, what happens if the leader abruptly dies? Someone trips and unplugs the master database.
The system has to heal itself. A coordination service, like Zookeeper, realizes the leader is dead. It immediately pauses all write requests, it checks the followers, looks at their transaction logs, finds the one with the most recent timestamp, the one that has the most up-to-date data, and promotes it. It officially elects it as the new leader.
It is a remarkable piece of automated crisis management, but single leader isn't the only way. You can also have multi-leader replication.
This is where every data center around the world has its own leader. If you're in London, you write to the London leader. If I'm in New York, I write to the New York leader. This is fantastic for collaborative tools like Google Docs, where people are typing at the same time. But conflicts are inevitable.
Let's explore that conflict. You and I are looking at the same folder.
Right. I rename a file to Project Draft Tone in New York, and at the exact same millisecond, you rename that exact same file to Project Final in London. Both of our local leaders accept the change. But a second later, the New York leader and the London leader try to sync with each other.
They collide. They have two completely contradictory pieces of truth. The system has to resolve it automatically.
How?
It might use last write wins, where it just looks at the timestamps and whoever clicked enter a millisecond later overrides the other. Or it might have a rule that the leader with the higher server ID always wins, but often the safest route is to not automate it at all. It prompts the users. There's a version conflict. Please select which version you want to keep.
Okay, so that's multi-leader. But then, throwing out the rulebook entirely, there's leaderless replication. Amazon's DynamoDB and Apache Cassandra are famous for this. There is no master node. Every node is perfectly equal. When you write data, it is blasted out to all nodes simultaneously.
But think about the logic there. Without a leader dictating the truth, how do you mathematically know if a write was successful?
You rely on a quorum. It's essentially a democratic vote. If you have a cluster of 5 nodes, your quorum is 3. As long as 3 out of the 5 nodes acknowledge the write, the system considers it a success and moves on. If 2 nodes are offline or busy, it doesn't matter. The majority rules.
But what if cloning isn't enough? What if that 100 terabytes is just too massive to fit on any one machine, even if you clone it a dozen times?
Then you have to slice the data up. It's partitioning or sharding. You take your 100,000 users and you physically put the first 50,000 in database A and the next 50,000 in database B. It sounds like a clean solution, but reading the sources, this seems to create an absolute nightmare called the hotspot problem.
It is the bane of database administrators.
Let's say we partition by alphabet. A through M goes to database 1. N through Z goes to database 2. What if, by pure coincidence, a massive news event happens and every single user whose name starts with an A, B, or C logs on at the same time? Database 1 is melting down, handling 100% of the traffic, while Database 2 is sitting completely idle. You haven't distributed the load at all.
You have to be incredibly strategic about your partition key. You usually use a hash function to randomize the distribution evenly. But partitioning introduces another issue, finding the data. If you partition users by their user ID, but later you want to run a search for all users who live in Chicago, how do you find them?
Because the Chicago users are scattered across every partition, you'd have to ping every single database and ask them to search their records. It's called a scatter-gather query, and it's horribly slow.
To fix that, you have to build secondary indexes. You either build a local index inside each partition, or you build a global index of a master map living on a separate server that just keeps track of cities. It says, if you want Chicago, check partition 3 and 7.
All of this complexity, replicating, partitioning, syncing across oceans, it brings us to the theoretical core of distributed systems, the CAP theorem.
This is the immovable law of physics for software architecture.
CAP stands for consistency, availability, partition tolerance. The golden rule is you can only pick two. You cannot have all three. But here is the massive catch. Partition tolerance means your system survives when a network cable is physically cut and servers can no longer talk to each other. Because we live in the real world where fiber optic cables break, routers crash, and networks always drop eventually, you are forced to have partition tolerance. It's non-negotiable.
Which means the CAP theorem really isn't a choice of 3, it's a choice of 2. When the network inevitably breaks, do you prioritize consistency or availability?
Okay, let's walk through a tangible scenario. Let's say I'm in New York and you're in Tokyo. We are connected to servers in our respective cities. Suddenly, a shark bites through the underwater transatlantic fiber optic cable connecting the US and Asia. The network is partitioned. The New York server and the Tokyo server can no longer communicate. Now, what happens if I try to update my bank balance in New York?
If the bank architect chose CP consistency and partition tolerance, the system's priority is absolute accuracy. The New York server realizes it cannot sync with the Tokyo server. It knows if it accepts your deposit, the two databases will be out of sync. So it refuses to answer. It goes offline. It says, sorry, system unavailable.
It would rather go completely dead than risk showing you a wrong, inconsistent balance. That makes sense for money. But what if we're on Instagram?
Instagram chooses AP availability and partition tolerance. When the shark cuts the cable, the New York server knows it can't talk to Tokyo, but its priority is uptime. So if you pull to refresh your feed, the server says, I know I can't get the latest post from Asia right now, and this data I have is probably 5 minutes old and totally out of sync, but I'm going to show it to you anyway.
Uptime is more important than strict real-time accuracy. A user would rather see slightly old photos than an error screen.
And that is the true essence of system design. It is not about building a flawless, magical machine. It is entirely about making deliberate, uncomfortable compromises. You have to willingly and knowingly break one part of your system, like real-time accuracy, to save another part, like 100% uptime.
I love that framing. It's about choosing with flaws you can live with. Okay, let's move to the next layer of complexity, managing chaos. We have load balancers, we have caches, we have heavily partitioned databases, we have microservices all over the globe. They're all shouting at each other constantly. Let's say a user goes on an e-commerce app and buys a pair of shoes. Think about the chain reaction. The app needs to update the inventory to reflect one less pair of shoes. It needs to email the user a receipt, and it needs to ping the warehouse delivery service to print a shipping label. How do we prevent this massive, tangled traffic jam of tasks from freezing the app while the user stares at a loading screen?
By understanding the crucial difference between synchronous and asynchronous tasks.
Walk me through it.
Updating the shoe inventory is synchronous. It must happen immediately, in real time, before you tell the user the purchase was successful. If you delay updating the inventory, you might accidentally sell that exact same pair of shoes to someone else a second later.
Okay, so the inventory update blocks the process until it's done. But what about the receipt email and the shipping label?
Those are asynchronous. The user does not need to wait for an email server to compose a message and send it through the internet before they see the success screen. That email can be sent 5 seconds later or even 5 minutes later.
So to handle those asynchronous tasks, we use a message queue. It's the fire and forget model. The checkout service updates the inventory instantly. Then it literally throws the send email task and the print label task into a message queue and immediately turns back to the user and says, order confirmed. The user is happy and moves on.
Meanwhile, behind the scenes, the message queue acts as a buffer. It uses a publisher-subscriber model.
PubSub. The checkout service is the publisher. It drops the message on the conveyor belt. The email microservice is the subscriber. It's sitting at the end of the conveyor belt, pulling tasks off the line and sending emails at its own safe pace. If there's a massive rush on Black Friday, the queue just gets longer. The email service doesn't crash, it just takes a little longer to clear the backlog.
There are different ways to configure that queue, though.
Right. You could use strict FIFO first in, first out. This guarantees the tasks are processed in the exact order they arrived. But there's a danger there. If the very first email in the queue has a glitch and fails to send, the entire queue stops and retries it, blocking the 10,000 emails behind it.
Which is usually a terrible architectural decision unless order is absolutely critical, like processing chronological financial trades. For emails, you use an unordered queue. It just grabs tasks continuously, bypassing failures. Or you use priority queues, where you can tag VIP customer orders to jump to the front of the line.
But what happens to the failures? Let's say a user entered a completely broken email address. The email service tries to send the receipt, it fails. The queue puts it back on the belt to retry. It fails again. It will loop forever.
These are called poison messages. They are toxic to the system's throughput.
To stop them from clogging the gears, the queue has a limit. After 3 failed retries, it throws its hands up and routes the poison message to a DLQ, a dead letter queue. It's essentially a quarantine zone, a graveyard for failed tasks. The main system keeps running smoothly, and tomorrow morning, a human developer can look at the DLQ, figure out why the email address broke the code, and fix the bug.
Which segues perfectly into how developers actually know things are failing in the first place: monitoring and fault tolerance.
Because faults are inevitable. Our sources break them down into 3 categories. Hardware faults. A server randomly catches fire. A hard drive corrupts. A rat chews through a power cable. Software faults. Deterministic bugs in the code that trigger under specific conditions. And finally, human faults.
The most dangerous component of any system.
A tired developer accidentally pushes the wrong configuration file to production at 3 a.m. and takes down half the internet. So you have to monitor absolutely everything. You track machine health, CPU usage, memory spikes, disk input-output, and you track API health throughput, error codes, and latency.
But the sources highlight a massive, very common trap when monitoring latency: the trap of averages.
Yes. Why should a developer never use the average response time to measure their application's performance? Because averages hide the outliers. Let's paint a picture. You have an app, and you have 10 users online. 9 of those users get a lightning-fast response in 1 second. But the 10th user, because their data happened to hit a bad server, waits 31 seconds for a response.
A terrible experience.
Right. But if you calculate the average response time for all 10 users, it comes out to 4 seconds. The engineer looks at the main dashboard, sees an average latency of 4 seconds, and thinks, it's a bit slow, but it's acceptable. They completely miss the fact that 10% of their user base just suffered a 31-second nightmare. The average completely masked the failure.
This is why professional engineers and major tech companies do not use averages. They use percentiles: P50, P90, P99.
Explain how a percentile gives a clearer picture.
If your dashboard says your P50 latency is 4 seconds, it means 50% of your users are experiencing load times of 4 seconds or less. That's your median. But then you look at your P90. If your P90 is 12 seconds, it tells you a hard truth. 10% of your entire user base is waiting up to 12 seconds.
And if you have 1 million users, 10% is 100,000 angry people.
Exactly. And the P99 targets the worst 1%.
Yeah.
Engineers relentlessly optimize for the P99. If you can force the P99 down to acceptable levels, it means you have guaranteed a smooth ride for virtually everyone, not just the lucky majority.
That is a phenomenal insight into how data can lie to you if you look at it through the wrong lens. So pulling this section together, when I buy those shoes and I close the app and then 2 minutes later my phone buzzes with a slightly delayed order confirmed text message, that's not a glitch. That's not the app being slow. That is just a message queue doing its job perfectly in the background.
Precisely. You are directly experiencing the intentional asynchronous architecture we just discussed. The app prioritized taking your money instantly and queued up the notification for later.
That is so deeply satisfying to understand. Okay, we have arrived at the grand finale. Let's take every single piece of this theoretical puzzle, the load balancers, the caches, the databases, the queues, and put them together to design something massive and real. We are going to architect a video streaming platform, a YouTube or a Netflix.
This is where theory meets reality. Streaming video at scale is one of the most punishing workloads on the internet.
Let's define the core problem. A high-quality 4K resolution video running at 60 frames per second for 20 minutes is massive. It's roughly 50 gigabytes of data. If a user sitting on a train with their phone has to download a 50 gigabyte file before the video even starts playing, your app is dead on arrival.
No one will wait for that. And frankly, most mobile networks would simply drop the connection halfway through anyway due to instability.
So the immediate solution is chunking. We do not send the whole file. We break that massive 50 GB video into tiny bite-sized segments, usually around 1 to 5 seconds long, and we use specific streaming protocols to send them, like RTMP over standard TCP connection. TCP ensures that packets arrive in order and verified delivery. But we don't just chunk the 4K file once, do we? Because 4K is still too heavy for a bad cellular connection.
Right. We have to introduce a transformation service.
The transcoding pipeline. A creator uploads their massive source video to the server. The server immediately throws that video into a priority message queue. Worker nodes, which are highly compute-intensive servers, pull the video off the queue and start crunching. They take that 1 second 4K chunk and they mathematically compress and transform it into multiple different resolutions. They create a 1080p version of that chunk, a 720p version, a 480p version, all the way down to a blocky 144p version.
They do this for every single second of the video. It generates thousands of tiny files. And this massive effort is what enables the absolute secret sauce of modern streaming, adaptive bitrate streaming.
I find this mechanism fascinating. When you tap play on a video, your video player doesn't just blindly ask for the file. It is incredibly intelligent. It continuously monitors your device's current internet bandwidth in real time.
It acts as an active feedback loop.
Let's say you're sitting in your living room on gigabit Wi-Fi. The player detects you have 300 megabits per second of bandwidth. It says, great, the connection is solid. Give me the heavy 4K chunk for second number 1. It plays beautifully. But then you get up and walk into an elevator. The thick metal doors close. Your Wi-Fi drops, and you fall back to a struggling 3G cellular connection. Your speed drops to 5 megabits per second.
If the player tried to download the 4K chunk for second number 2, the video would instantly freeze and buffer.
But it doesn't freeze, because the player instantly detects the drop in bandwidth. Before second number 2 even starts, it pivots and seamlessly asks the server for the lightweight 480p chunk instead. The video quality drops, it gets blurry, but the playback doesn't stop. Then you step out of the elevator, your phone catches a 5G tower, your speed spikes, and for second number 3, the player dynamically requests the 4K chunk again. The picture snaps back into sharp focus. This intense orchestration happens automatically second by second, entirely behind the scenes.
It is a brilliant solution, but we have one final bottleneck. Where are all these millions of chunks actually stored? If everyone in the world is downloading video chunks from one massive server farm in California, the latency to India or Australia would be unwatchable.
Which brings us to the CDN, the Content Delivery Network. A CDN is essentially a massive, globally distributed network of cached servers. When a video goes viral in Mumbai, the core servers in California push all those tiny transcoded chunks to edge servers physically located in Mumbai.
They are caching the video as close to the user as physically possible.
So 1 million users in India are fetching the video data locally from a server just a few miles away, which drops the latency to near zero. And what about the comments, the likes, the video title? The NoSQL document database we talked about earlier handles that. It stores all the unstructured metadata globally.
So if we step back and look at the whole picture, the DNS routes you to the closest data center. The load balancer checks server health and hands you to the least busy web server. The NoSQL database provides the video title and comments instantly. The CDN Edge server streams the transcoded chunks to your phone, while your player uses adaptive bitrate logic to negotiate the quality based on your cellular signal.
All of it working in perfect harmony, scaled globally, protected by caches and queues, to handle 100,000 simultaneous viewers without a single dropped frame. It really is a beautiful symphony of engineering. Every component we unpack today plays a critical, irreplaceable role in making that single video play smoothly on your screen.
It's a testament to decades of iterative problem solving. Every bottleneck spawned a new architectural innovation.
It is breathtaking when you really see the whole board. And that brings us to the end of our deep dive. We've covered an astonishing amount of ground today. We've explored the sheer scale and the invisible complexity of the systems we interact with every single day. From the desperately overwhelmed cashiers at the Alien Bank, teaching us about the limits of vertical scaling, to the intricacies of database transactions, and finally to the adaptive bitrate streaming algorithms that are literally delivering this very audio to your device right now.
We hope diving into these mechanics gives you a new appreciation for the digital world around you. It's easy to take for granted until you understand the sheer force of will required to maintain it.
Absolutely. But before we sign off, I want to leave you with one final provocative thought. We've spent this entire hour talking about how giant tech companies build massive, centralized server farms, the cloud. We talked about moving data from your device up into these colossal data centers to be processed by load balancers and message queues. But look at the current rise of edge computing. Look at the sheer processing power of the neural engines currently sitting inside your phone, or the advanced chips going into local Wi-Fi routers. What happens when the processing power leaves the centralized data center entirely? What happens when your device is powerful enough to do the heavy transcoding and database querying locally? Will the massive centralized cloud architectures we just spent an hour designing become a relic of the past? Will the internet decentralize back to the edges?
That is the ultimate frontier. As we established today, the architecture always inevitably evolves to meet the next bottleneck.
Something to mull over the next time you tap an app icon and wait a millisecond for the magic to happen. Thank you so much for taking this intense journey with us today. Next time you're stuck waiting for a 4K video to buffer, just think about the millions of microscopic decisions happening to get it to your screen. Until next time.